Okay, so picking up where we left off in section 13.1, before we were given a formula and we plugged in, 1, 2, 3, 4, and so on to find the terms for a sequence. Now we're going to work backwards. I'm giving you the terms, we're going to work backwards to find the formula. Okay, so again, think about, starting at 1. So this is the first term, this is the second term, this is the third term, fourth term, fifth term. So knowing that that's the first term, that's the second, that's the third, that's the fourth, that's the fifth, what can we do to these numbers to produce these numbers? Well, you might see that these are all squares. So 1 squared is 1, 2 squared is 2, 3 squared is 9, 4 squared is 16, and so on. So our general formula is n squared. Okay, let's look at another one. This one looks pretty easy with the 1, 2, 3, 4, 5, 6, but we have these alternating signs. Now you might remember that I gave you some formulas for how signs alternate, be it if the whether the negative starts first or if the negative is second, how it alternates. So we're going to handle those separately. We're going to do the sign alternating in kind of one formula and then the other numbers in another formula. The 1, 2, 3, 4, 5, 6, that's easy enough. That's just n, right? Because that's the first term, second, third, fourth, fifth, sixth. Easy enough. The alternating starts with positive, negative, and so on. So I'm going to use this formula, this n, negative 1 to the n plus 1. So we can see that if we start with 1 right here, that's going to be negative 1 to the 1 plus 1, which is 2. So negative 1 squared is a positive 1. And then this over here is just going to be, 1 when we plug in 1, and then 2, 3. So this is the 1, 2, 3, 4, 5, 6. This part right here is controlling the alternating of the signs. All right, this one's a little more difficult because of the fractions. So you should pause the video and see if you can come up with the formula for that one. So let's write it as like 1 over 1, 1 over 8, 1 over 27, 1 over 64. Anything that's staying the same is going to remain in the formula. So this 1 on the top is going to stay on our formula because it's constant. The numbers down here, so if I plug in an n value of 1, or an n value of 2, an n value of 3, an n value of 4, I get those denominators. So I know my numerator is going to stay the same. It's just going to be 1. But what do I have to do to these n values in order to get that denominator? Well, let's see. This one stays the same. But these don't stay the same. You might recognize these. These are the perfect cubes. So this is going to be 1 over n cubed. Because if I take 1 cubed, I get 1. If I take 2 cubed, I get 8. 3 cubed is 27, and so on. Now, some sequences are not as easy to define as these. Some of them are going to be defined recursively. That means that we're going to have to use a previous term or terms to define the future term. So let me show you what I mean by that. So this first one is an example of a recursive sequence. So this is telling you the first term is 2. This is telling you the formula for the future terms. Now you'll notice that these are different. This is saying that whatever term you're looking at is 5 minus the term right before it. So let me show you, but just plugging in some numbers here. We know the first term is 2. The second term, a sub 2, so I'm just plugging in 1 for n. That makes that 1 plus 1, which is 2. Plugging in 1 for n. So a sub 2 is 5 minus a sub 1. Well, we know a sub 1 was 2. See how I kind of color-coded those for you? So 5 minus 2 is 3. The third term, a sub 3, now I'm plugging in 2 for n. So that's all I'm doing is, 1, 2, 3, 4. So I'm plugging in now 2. So 2 plus 1 is 3. 2 goes right here. A sub 2 was this number. Was this 3. So it's 5 minus 3, which is 2. A sub 4 is 5 minus a sub 3. And you can kind of see what this sequence is doing. It's just bouncing back and forth between 3 and 2. Now, not all recursive sequences do that. This one just happens to. Okay. So let's look at this recursive sequence. This one tells us that the first term is 1, the second term is 1. After that, the future terms are the sum of the two previous. So for instance, if I plug in 1 right here, I'm going to get a sub 3. If I plug in 1 for n, a sub 3 is a sub 1 plus a sub 2. So this sequence is telling me that a term is equal to the sum of the two previous terms. This is what's called a Fibonacci sequence. So we get that a sub 1 is 1, a sub 2 is 1, that was given to start with. A sub 3 is a sub 1 plus a sub 2, so 1, 1, 2. A sub 4 is this 1 plus 2. So this is what's called a Fibonacci sequence, and the terms are found by taking the sum of the two previous ones. So 21 was found by 8 plus 13. Okay. Let's talk about factorials. So a factorial looks like an exclamation point, but this is actually read 5 factorial. Okay, it's not read 5. And this little factorial symbol, so exclamation point, is an abbreviation that's telling you to multiply 5 by every natural number all the way down to 1. So 5 factorial represents 5 times 4 times 3 times 2 times 1, which is the number 120. So 4 factorial, that's 4 times 3 times 2 times 1, which is 24. 3 factorial, 2 factorial, 1 factorial. And then 0 factorial, you probably assume it was going to be 0. Most people would, but it's actually 1. That is a definition that we use. We can end up, I usually end up kind of showing you how that's true in maybe like a probability class maybe. But yeah, we don't really have to worry about it. You can maybe just like take that on faith as great mystery of the universe, like Area 51, Stonehenge, how to fold a fitted sheet, 0 factorial, all mysteries of the world. Okay, so let's talk about how to evaluate these. So if you have 18 factorial over 16 factorial, you cannot just ignore the factorial symbols and reduce 18 over 16 and then do the factorial. Okay, so instead 18 factorial would be 18 times 17 times 16 all the way down to 1. Whereas 16 factorial would be 16, 15, 14, all the way down to 1. So in writing all that out, once I get this kind of written out to multiplication, now I can cancel it. That 16 over 16 is going to be 1. That 15 over 15 is going to be 1. So all these are going to cancel all the way from 16 down to 1. And I'm just left with 18 times 17, which is 306. Okay, so let's see how that works on a calculator. So the factorial button, if you go under the Math menu and go all the way over to Probability, I'm just going to do the left arrow so I can jump over there. You can see option 4 is the factorial key. So if I was to do 18, Math, Probability, Factorial, you can see it's a big honking number, right? That's E right there. That little E is scientific notation for times 10 to the 15th power. Big honking number. So if I divide that by 16 factorial, you can see I get 306. Now I could have done that without hitting enter along the way. So I could just type it in just like that. Now, as these numbers get bigger, your calculator's not going to be able to handle it. Because as you saw, something as small as 18 factorial got really big. Okay, factorials grow super quick. If you tried to put this one in your calculator, if you tried to do 100 factorial, it gives you an overflow error. It's like, no, not today. All right, so you're like, cool, let me just do 100 factorial divided by 98 factorial. Maybe it can do that one. Nope, can't do that either. Strangely enough, the calculator can't handle it, yet you can do this in your head. So if you know the factorial symbol just represents multiplying by 100 times 99 times 98 all the way down to 1. 98 factorial is 98, 97, all the way down to 1. These 98 down to 1 will cancel, and you're just left with 100 times 99, which you can do in your head, right? 9900. Booyah. Now we can have, more than just a factorial on the top and the bottom. We can have like a multiplication here. You know that smushing right there means multiplication. So we can have something like 20 over 20 factorial over 2 factorial times 18 factorial. You can do this on the calculator. You want to be really careful, though, how you do that. So let me write it out first, and then I'll show you. So 20 factorial is going to be 20, 19, 18, all the way down to 1. 2 factorial is just 2 times 1, and then 18 factorial is 18, all the way down to 1. So my 18 down to 1's canceled, and I'm just left with this bit right here. So 20 times 19 divided by 2. I went ahead and did 20 over 2 and got 10, and then 10 times 19 is 190. So let me show you what happens on the calculator here. So if I do 20 factorial divided by 2 factorial times 18 factorial, angle this just right. So there's the original problem. Look what happens. That's because the calculator is going to go left to right on those order of operations. So it's dividing by 2 factorial and then multiplying, so it's bringing that 18 factorial up. So what you can do is put parentheses around that entire denominator. That tells the calculator, hey, all of this is my denominator. Now, in case you wondered how I did that so quickly, if you hit second and then enter, where it says entry right there, it will bring up the last thing that you typed. So I hit second, enter, brought it up, and then was able to edit it by hitting the insert. So if I wanted to go back. So it looked like that, so I went back here, and I can't just type a parenthesis because it'll automatically type over it. So I had to hit second and then that INS to insert that parenthesis right there. So don't you thinking it was some kind of witchcraft that was going on here? All right. Now, the factorials can be used in sequences as well. So let's write out the first 4 terms of this sequence. So pause the video. You know how to do this. You plug in 1 for n, you simplify it, there's your first term. You plug in 2 for n, you simplify it, there's your second term. So pause the video and write out the first 4 terms of this sequence. Okay, so a sub 1. So you can see where I'm plugging in 1 here. I get 1 plus 1, which is 2 factorial. 2 factorial is just 2 times 1. So I have 2 times 1 divided by 1, which is just 2. All right, next up, plugging in 2 for n. So I get 2 plus 1 over 2 squared. That's 3 factorial, which is 3 times 2 times 1. Now, if you want to use the calculator for that, that's fine. Just for some of these smaller factorials, I just assume do them in my head. So I got 3 times 2 times 1, which is just 6, and that's over 2 squared, which is 4. 6 over 4 is 3 halves. Next up is 3. So I have 3 plus 1, which is 4 factorial, over 3 squared, which is 9. 4 factorial is 4 times 3 times 2 times 1, so that's 12 times 2, which is 24. So 24 ninths reduces to be 8/3. Now, if you wanted to do this in the calculator, you certainly could. If you wanted to do 3 plus 1 math factorial, oop, had my angle off here so you can't see what I'm doing. 3 plus 1 and then factorial, and that's divided by 3 squared. So you can see it gives you a decimal, but if you go to math, fraction, hit it again, you get 8/3. So you certainly can do this on the calculator in case you get a little stumped. And then lastly, the fourth term, plugging in 4, we get 5 factorial over 16. 5 factorial is 120, and then 120 over 16 reduces to be 15 halves. If you have trouble reducing that, or you're just feeling kind of lazy, you can do 120 over 16, and then math, hit fraction once to bring up the command, fraction again will execute the command, and there it is, 15 halves. All right, so that concludes section 13.1.